It's my pleasure to have Neil Lawrence come and give us a talk in the first of our autumn series of Advances in Data Science seminar series. I've known Neil for a long time. Neil was doing a PhD in the group where I did my first postdoc, and he went on to great things. He's developed and contributed to many great developments in probabilistic machine learning. For example, the GPLVM was an early paper in Neil's single author paper, I think, so he definitely did it.
Single author. I definitely did it, or I managed to get rid of whoever I collaborated with.
And he's done a lot since then. So he spent a lot of his academic career in Sheffield as a lecturer. Then he came over to Manchester for a period. We stupidly lost him back to Sheffield. We lost me there as well at the same time. And Neil and I had a group together for a couple of years in Sheffield. Then I returned and Neil stayed in Sheffield, and then he went to Cambridge to work first in Amazon research. And then recently he's become a chair, I think the DeepMind chair in Cambridge. And it's my pleasure to have him come and talk about deploying machine learning, intellectual depth, and AutoAI.
Thanks, Magnus. And great pleasure to kind of be here, but not be here. But I feel like I'm in Manchester. I know what Manchester looks like. So I wanted to talk to you about today, as Magnus mentioned, I started in Aston with Magnus, I guess, wow, nearly 25 years ago. But I've since been working in machine learning that long, but recently I had this 3 years at Amazon, which was really very purposeful to try and see what's going on in terms of deployment of machine learning algorithms. And the project I'm going to talk to you about today is funded by an ATI Senior Fellowship at the Turing Institute, Senior AI Fellowship. And it really is trying to sort of address some of the challenges that you see when machine learning systems are deployed. So there's not going to be so much in terms of solutions, more a roadmap of what I think we can do, but it's also a sort of open invitation to come in and join in this agenda, which is actually how we get safe, reliable, deployed machine learning in practice. So I guess when machine learning somehow became AI and everything exploded, I suddenly discovered that I was now considered to be an AI researcher, although it wasn't the field I joined. When Magnus and I were starting in it, it was called neural networks, then it sort of became machine learning. But it meant that I got lots of questions about what AI was going to be like. And it's interesting because people have different perceptions about what artificial intelligence is, I think, depending on whether you're working in the technologies or a member of the public. But one thing I think that these perceptions perhaps have in common is this slightly idea that it's going to be the first generation of automation to adapt to us rather than us having to constantly adapt to it. So if you look at previous generations of automation, such as factory systems or even trains or automation with movement, we tend to have to adapt to the machine. And the sense I get when people are thinking of AI is they have this image of sort of Jeeves. So I've shown this sort of drawing of Jeeves and Worcester with this subtitle, right from the very first day he came to see me, I have looked on Jeeves as a sort of guide, philosopher, and friend. So I think we see AI as being something perhaps beyond just this automation of decisions and more to do with this ability to be a companion. Now, that to me implies that this automation will adapt to who we are as individual humans. And I just think that there's absolutely no evidence that we've created anything like that. Indeed, I think that the separation between that perception that that's what we've created and the actuality of what we've created is highly problematic. So I call this the great AI fallacy, that as if we've suddenly invented something radically new, and we absolutely haven't. But what we are trying to do is start deploying this in environments where there's a lot less control in the environment of which we're deploying. So the notion that we can create something that can adapt to us means that we're somehow assuming that we can take these ideas and just deploy them on the street. So robots that walk around us or something like this, or driverless cars that just drive within our cities. And I think this reflects something about our natural intelligence, that of course we're very capable of doing this ourselves. But there's a really big and important difference between natural intelligence, or a natural system in general, whether we consider it intelligent, and the artificial system. So the artificial systems are designed, whereas natural systems are evolved. And so what are the implications of that? Well, people think of evolution as perhaps survival of the fittest. You can try using the chat here. Can anyone type in the chat who that quote is from? That's normally I would ask and you would answer, but in this new world, you type it into the chat. Come on, someone have a go at typing into the chat. Who said that? Darwin. Thank you, George. Thank you. That's exactly what you're supposed to say. Very kind of you, George. Yeah, excellent, Charlie. That's good. So yeah, it wasn't actually Charles Darwin, and that's kind of the point of that little bit. It was, I've got a private message that was Magnus. Yeah, well, could have been. There's actually a guy called Herbert Spencer, who was a sort of follower of Darwin's and a great advocate of his ideas. But I think it's just utterly non-representative of the way evolution works. In practice, I think a better term, and I came up with this term, but unfortunately someone else, it turned out, had come up with it before, so it's something else other people have said, is a better thought is that evolution is non-survival of the non-fit. So meaning in evolved systems, you don't succeed by being the very best at something. It's not like the very fastest runner. You end up failing because you fail to take account of something that in the real world punches you. I like this sort of Mike Tyson quote, which actually he made before he lost a fight. So it's not a great quote. Is everyone has a plan till you get punched in the face. And it's a quote that's derived from some Prussian general who has, I think the original is something like, no plan survives contact with the enemy, which was a Prussian general in the 19th century. But the basic idea is the same, that you plan things, you design things, you deploy them in the real world, and the real world sort of punches you in the face. It does unexpected things because it's a non-controlled environment. And that's what determines, that's the main driving factor, I believe, in terms of the type of systems we see naturally, that they're robust to being punched in the face. I mean, obviously, creatures die, they make errors, but their survival is determined by their failure to make errors, as it were. Some double negative there, rather than their performance at a particular task. And in terms of when we're thinking about artificial systems, we make an enormous mistake, because that sort of style of fitness, we seem to equate it for an objective function, as if there's a known mathematical thing that we can write down and optimize, and then we're going to perform in the real world. And the just real world totally isn't like that. The real world doesn't have a static environment and known objective. Indeed, if you look at previous attempts to automate, a lot of the effort goes into creating a static environment around the automation. So building a factory or building a railway line, banning people from cycling on motorways, this type of thing, controlled environment so that we can automate and scale the way in which we're doing things. There's a question from Barkey. Do you want to come in or just type it into the chat? I don't know. Are we all handle questions? Or was it an error? Accidentally pressed hand raise. Okay, I'll carry on. Type questions into the chat if there's something that's not clear. Okay, so that's sort of point one, that we haven't overcome this. We haven't suddenly found ways of creating sort of natural systems. Now, the next thing I want to mention is, and I was struggling for a term for this. In fact, when I wrote the proposal for the Turing AI Fellowship, I didn't have this term, and I was talking about it with Bill Thompson, who's he's a BBC journalist, and he does is it Click? It's still called, I can't remember its current name, but he does a podcast on BBC and is a technical expert. And I was describing this to him, and he said, "Oh, well, that sounds like what Jonathan Zittrain calls intellectual debt." And then he explained what intellectual debt was, and you can see it on this Medium post. Most of Medium seems to be filled with rubbish, but this is a very good Medium post. and very well worth reading. The notion of intellectual debt, which I think is a massive challenge in this environment, because what we're doing is we're building and deploying AI systems into an uncontrolled environment. And we don't have the capabilities for those systems to sort of self-heal or adapt to the environment. So what it becomes very important is that we are capable of understanding when things have gone wrong and fixing those things rapidly. And intellectual debt is a really nice term that is going to capture that challenge. So I'm going to explain a little bit about what intellectual debt is. So perhaps you might have heard of the notion of technical debt. So technical debt is a sort of software systems term, which D. Scully and others from Google highlighted as something that is associated often with machine learning systems. So in technical debt, the idea is you build a large and complex software system, and you don't know whether you're going to get lots of users. So you sort of build it quickly and you deploy it, but you don't necessarily always get the engineering right for maintaining that system as the number of users goes up. So because you weren't sure whether your idea was going to be successful, you had a small startup, you didn't build a system that is capable of handling sort of millions of users, and then you end up spending a lot of time on software maintenance. And D. Scully and others were highlighting technical debt as an issue. And it's an important and interesting issue. And it's actually dealt with very often in software systems by separation of concerns. We'll come back to that in a moment, but it's a big principle between software design to try and ameliorate technical debt and ensure that you can build scalable systems. But how does that relate to intellectual debt? Well, so intellectual debt is very similar, but technical debt is the inability to maintain your complex software system. Intellectual debt is the inability to explain your complex software system. So what do I mean? Even if you've built a system where you're not having to do software maintenance to, as people used to keep saying in Amazon, keep the lights on, it doesn't mean you've got a system that you can explain what's going on. And my favorite example of this would be, I think I can never pronounce this right, but in the Technonomy 2016 conference 4 years ago, shortly after the US election, Mark Zuckerberg said it was a crazy idea that fake news might have in any way influenced the US election. 11 months later, when giving evidence to Congress, I believe the evidence contains information that up to 76 million US citizens saw fake news produced by the Russia-based Internet Research Agency as part of a massive sort of large-scale production of fake news designed to, whether it was influence or sort of confuse the election, not clear, but certainly fake news was very prevalent within the Facebook system. And it's not that Mark Zuckerberg sort of knew this and was covering it up. I don't believe that's the case. If that was the case, then this is great because it's a conspiracy. We can arrest people and bring an end to it. The real challenge is this intellectual debt that people in Facebook didn't know that this is happening. Just like Google are in a constant battle to deal with adversarial attacks on their search engine rankings. So this whole process of search engine optimization, which in effect is a commercial thing now. The reason Medium blog posts, despite their poor content, often come to the top of your search is because they've effectively gained the search engine optimization by having a massive interlinked website that Google will always rank highly, apart from Jonathan Zittrain's very good post. So being able to explain and understand that is extremely difficult, particularly in an uncontrolled environment. So let's talk a little bit about how this looks in practice on the sort of system we might try and build. And what I'm going to use as an example is a sort of automated buying system. And why I find these examples interesting is because they do something that I sort of became slightly obsessed with while I was at Amazon, which is the prevalence of demand and supply and matching those two as a requirement for automated system building. So this is known as supply chain modeling, and it's very, very common in operations research as a task. And actually one reason you can tell that the sort of AI systems we built are pretty crap is because they do not dominate operations research in automated decision-making systems like this. So these type of systems they'll have statistical models in, they'll have control systems models, they'll have machine learning models in, and also, you know, there's an increasing amount of, say, machine learning coming into it. So in a buying system like this, the objective is of any large-scale automated buying to understand, you've got some stock, so you might be selling paper clips, and what you need to understand is what the demand for paper clips will be, and what the supply of paper clips is likely to be. So you maintain a stock. I had this wonderful colleague who called Narayan at Amazon, who once told me the whole magic of supply chain is making it appear as if everything grows on trees. So if you want a paperclip, you just go to a store and they have them. Of course, they're not made in the store. And okay, paperclips are a bad example, but let's say you want a laptop computer. They take a certain amount of time to build, but you don't have to wait that amount of time to buy them. And that's because someone's done a demand forecast, a supply forecast, and they maintain a stock. And that whole stock is dependent on what the demand is likely to be. And when you get things like COVID, it messes with everyone's stock and things go out of stock. And it's actually amazing how quickly everything comes back into focus. It's not surprising at all that toilet paper disappears and these sort of things. So in this sort of automated system, you have the demand forecast, the supply forecast. These are combined in some way, including a cost basis, what's your cost of storage, etc., to make your predicted stock. And then you can make a rectification action, so you can make purchase orders to sort of try and improve your stock to hit the level you want. Now, how's this done? Well, traditionally, work like this would be done in perhaps a monolithic piece of software. Actually, it's funny, today we've seen that news story that everyone's shocked about, that people have been using Excel to process data. I mean, Excel is everywhere in supply chain, not in Amazon's supply chain so much, apart from a sort of way of seeing end results. But many major supply chains are run almost entirely on Excel, in the same way that those test results were being stored in Excel. So the data systems around this aren't that great. But if you were to write a program, historically, the sort of program you might have written is what we would call a monolithic piece of software, so a bespoke piece of software. And that's what I'm trying to show here, where you've got all those little bits and pieces inside the same box. And I mention this because it's an important part of, I was lucky enough to be interviewed when I joined Amazon by a guy called Peter Voschel. And what Peter Voschel did was he was responsible for taking the Amazon website, which was also a monolithic system, the page renderer. In the early noughties, it was sort of becoming overloaded, and converting it to what we would call a modern service-oriented architecture. So the whole of AWS, Amazon Web Services, is sort of founded on the idea that instead of using a monolithic piece of code, which would be like something like Excel or Word or an operating system, millions of lines of code, and you separate the software up into smaller services like this. So you've got the demand forecast, and then that's joined together with the supply forecast, and that's then pushed into cost predictions, and then that's pushed into a purchase order. So these things link together in some way, but each of these things is a separate service and a separate code base that is often managed by a separate team. And this is the way the modern Amazon website works, and the way AWS organized software tends to work. And that's, of course, not restricted to the buying problem. We can also take this type of supply and demand and think of something like banking, where in banking, we might have a request for a loan. And then once the loan request comes in, we're going to look at what the forecast perhaps for that customer's expenditure is, and maybe a forecast for what their income is. And then we might use that, combine that together to offer some loan terms. Now, the reason I switched it to a banking example is when we're in the domain of the purchasing example, well, you might not worry too much. There's probably some personal information hidden in the demand forecast somewhere, but it's typically aggregated and going to be anonymized. So that's not really a problem. Or the supply forecast is coming from modeling manufacturers and how quickly they can supply goods. So again, there's little personal information there. So the buying example is not an example where there's a lot of personal information going around. And the decision that's being made here in terms of the purchase order is not what one would term consequential in terms of, say, the GDPR. So if you look at legislation around decision-making and data, there's this notion of a consequential decision, and that's one that has a sort of material effect on the individual. And I think one would argue, okay, so I may be upset if there's no paper clips on the site, but I don't think I can argue it's a consequential effect. Whereas whether or not I'm granted a loan, or whether or not I'm given a place at university, this can have a consequential effect. And most so-called data protection legislation, I say so-called because it's an appalling name, it's really personal data rights is what you're being given through those acts. Legislation is concerned with this type of consequential decision making. So the problem with this intellectual debt thing is you've got all these decisions going on that are having these downstream consequences that are feeding back into your system, and you don't even know it's happening. So, you know, how does Mark Zuckerberg worry if his large social network is having this effect on the election? Well, he doesn't even know until 11 months after the election, because these systems have become so complicated because they're built in this way where we can build them component-wise that basically no one understands them. So that comes back to this term separation of concerns. We can build these complex systems because we choose to separate the concerns, but the result is no one's concerned about the whole system. So there's no one there who's worrying about these issues around well, people do certainly worry about consequential decision making, but it's not easy to sort of see the downstream effects of all these decisions and see when society's acting in a strange way or your system's being manipulated. You know, the manipulation of Facebook to bring about fake news is very similar to the manipulation of search engine optimization, you know, in terms of these systems are being deployed in the real world, and the real world sort of punches them in the face in some way or another. Okay, so, well, why is that important? Well, I like to use this example of SafeBodder. I haven't met this team, but it was an example I started writing about as a potential example when I was writing the fellowship proposal of, imagine you want to do a ride-sharing system in a city such as Kampala. So a ride-sharing system is again, matching supply and demand. Here, there's a demand for riders. So what you're keeping in stock is the number of, a demand for drivers, the number of drivers you have on the street, like Uber have, and they have pricing systems for getting more drivers out. And you've got some idea of what you expect demand for those drivers to be. And you can control to some extent the supply of drivers. So again, it's matching supply and demand. And I was very interested in, if you go to Kampala, or I think also Lagos, I mean, many major African cities, there's a system called Boda Bodas. So I think we've got some of my African colleagues on the call I saw joining earlier, so they'll sort of know about this, that it's a ride sharing system where you ride on the back of a motorbike, and the motorbike riders are often young men who use this for work. They rent their motorbike and they sort of sit on street corners waiting people to grab a ride. But they often don't supply helmets, or here you've got sort of helmets and high visibility tabards. And the idea behind SafeBodder is that there's a sort of mobile phone app that tries to make this safer. So here's a quote from their website. With road accidents set to match HIV/AIDS as the highest cause of death in low middle income countries by 2030, SafeBodder's aim is to modernize informal transportation and ensure safe access to mobility. I think this is a great aim, and it's a very exciting idea. And what I want to see is lots of ideas like this coming up in Kampala, coming up in Accra, in Lagos, in the capital cities where they're having these problems. But if we're in a situation where companies the size of Facebook don't understand when their complex AI systems are being manipulated, we're basically in a position where we can't expect small teams of software engineers, where there's perhaps not the sort of liquidity of software engineers certainly Nairobi and Lagos have really good tech bases, but not every city does. So you want 2 or 3 software engineers to be able to build such a system, to get together and deploy and maintain and explain the AI system they're building. And that's really the motivation for this AutoAI agenda that we have. of course, once you've done that, as long as you've got sort of two, nicely qualified master students from, say, the University of Makerere and Kampala can do it, then anyone can do it. That's really the idea here. But what we have to do is start, I think there's a major problem in machine learning is that we're not looking at how these things are deployed in practice. We're not understanding what the issues are and how they're being scaled. So my big example would be in machine learning, the current focus on things that we need to get right, like the fairness, accountability, and transparency of these things. All of these things not being in place are a consequence of intellectual debt, that we're deploying systems we don't understand. It's being applied to individual models. So we try and get a better understanding of a single neural network in how it's making decisions. Well, sure, that's important. But whenever you look at how these systems are being built in practice, an individual model isn't the problem, because all of these systems tend to be a composition of multiple machine learning models or multiple decision-making systems all at the same time. So if we look at the ride allocation example, there'll be a large number of things going on. There'll be the sort of traffic map, there'll be the maps, there's pickup status of people, there's driver locations, there's current journeys. All the boxes you see on the right are sort of known data. And then you've got a load of predictions going on, predictions around what the wait time. And of course, that prediction is dependent on information that we do have within the system. But over time, we don't know the wait time of someone when they request a ride, but we can see within our system what the previous wait times were in the past. So somehow this is information that's contained within the system, that's moving around the system. And we want to really understand a lot better how those decisions are being made, what's influencing what. Like, are we making a decision on future wait times dependent on data that's coming from a corrupted period, such as there was a big football match on, or the sort of things around COVID, because you want to be able to identify that quickly? Or are you seeing suspicious activity where your wait time system is being gamed? Now you need to be able to monitor when that's happening. Okay, so I'm going to outline the sort of solution. Comment there, Amazon listings ranking of products might fit into this discussion. Yeah, absolutely. I mean, totally. So you've got the same type of problem within the large databases such as the Amazon catalog. A lot of the Amazon catalog is filled in by sellers who introduce products to the catalog themselves. And of course, constantly one of the things that Amazon spends a lot of time dealing with is, say, fraudulent sellers and trying to notice when they're being gamed. As soon as you deploy any system into the real world, people will try and game it. Yet most of machine learning work is about a static system. Okay, so I don't think we can go as far. Like, my real dream would really be, it just didn't seem sensible for a 5-year project, would be to get a better handle on building systems that look a bit more like natural systems. I mean, Magnus mentioned we worked together. We did a lot of work on computational biology together, particularly across the period I was in Manchester and Sheffield. And the really thing you see about a natural system is things like the redundancy. It's amazing how much manipulation. There's this sort of famous paper, Can a Biologist Fix a Radio, which is all about how you might study a biological system and what it might look like if you were studying a radio. So that the idea is that the first thing you do is you destroy a component of the radio and see what happens. Well, if you try that on a radio, it won't work. But it's extraordinary how many biological systems, if you knock out a gene or knock out a functionality, they will survive and they'll have a different phenotype. Something may change or it might not, because there's a lot of redundancy in those systems. And there's not a lot of redundancy in the systems we're producing. Now, that's a separate question. I'm not going to try and address that sort of redundancy thing. I do think that's fascinating. And that's probably long-term the real answer. But I see very little work on formalizing that for the moment. So instead, I'm going to introduce you to the sort of idea I actually spoke about when I was interviewing with this guy, Peter Voshall, at Amazon. And something that was in my head when I sort of went into Amazon, mainly driven by this experience of Data Science Africa and what the problems were in building end-to-end machine learning systems there, which is what ended up being called data-oriented architectures. It's also been called data as a service. So actually, I should go straight to this first. So the idea here is to provide what I might think of as a tube map for the data. So try and provide a map where you understand what all the flows are of data throughout your system. And by data, I don't just mean the input data, I also mean the predictions that you're making. So each one of these components that you have is tending to make a prediction about the wait time. That's now a data stream within the ecosystem. And what the idea is that you build a streaming algebra. So streaming algebra would be a category theory based language that at the moment we call the Milan intermediate language. And there's an implementation of this. I should say, by the way, I've got, and I'll show you at the end, there's full notes about this talk. If you search for Neil Lawrence talks, you'll see much more detail about what I'm saying in on my website at the top, where I talk and give links to blog posts from Tom Borkert, who's been the main architect of Milan, about this project. So the idea in Milan is that this is a sort of systems description language. So the intermediate language in Milan, which is the thing in the sort of cyany blue box in the middle, describes what data connects to what. And it does so in such a way that we can compile that description into something that can then be implemented in something like Apache Flink. For those of you who don't know, so Apache Flink is a commonly used approach to sustaining the modern versions of these service-oriented architectures, which are in effect called streaming architectures. So they're called streaming because data is constantly flowing between these different services. So Apache Flink is a sort of an open source implementation of the joins of these data. And Apache Flink does indeed describe how data is joined, but it does so in such a way that we can't necessarily untangle what's joining to what. So the Milan intermediate language is a restricted language that allows us to see what's joining to what. In fact, it lays out the map that we've seen in these slides here. So this is showing how data is flowing from one place to another. But of course, in practice, it's going to be much, much more complicated. So that's what the intermediate language does in Milan. But the aim is that then that can compile to some standard streaming framework. And it can also be written, not in the intermediate language itself, but in some language such as Scala, which is a typical language people might use for building these data systems. Or of course, we might want Python. Everyone is using Python a lot. So at the moment, the first version of Milan just implements these three, but it's easy to sort of extend it and have it so that you can describe how the data joins occurring in Python and translate that to an intermediate language, which is then compiled to Apache Flink. Or another streaming framework, which I think this one's more targeted at IoT devices, such as RabbitMQ. So the aim is that the Milan intermediate language provides a roadmap that allows us to do things like AutoAI, because it's telling us what the landscape of what data is joining to where. It also allows us to, one of the challenges if you work in a company is explaining to your business lead, just as explaining to Mark Zuckerberg what's going on in Facebook is a challenge, how things are connected together within the underlying ecosystem, because they're not doing the code. So they're always asking for sort of architecture diagrams. And at the moment, very often, if you're talking about how services are connected together, they have to be manually recreated. Which means talking to every software team that's built these subsystems. But here you'll just be able to compile what that diagram looks like and show, look, this is the basis of that decision. The decision you're asking about, why did we buy 29,000 tiddlywinks from Hong Kong, is because of these 17 inputs. And then we can start looking at the problem. But also things like sharing this information with the Offices for National Statistics, if they're interested in such information because they want to know about movements or purchases in COVID, they want to understand how non-pharmaceutical interventions are affecting the economy. That's the sort of thing in the future we can imagine the Office for National Statistics being interested in. And of course, the ICO is going to be interested in these type of decision-making frameworks because they're interested in whether we're conforming to regulation around personal data privacy. Or we might also be interested in as long as we're not infringing intellectual property rights of people in the system. So that intermediate language is really, really critical. And there's a sort of BSD licensed version of that you can find online. And you should feel free to download and play with that. That's something that I believe internally Amazon are continuing to develop, and we're really looking to sort of build on these ideas in the ATI project. So that's on GitHub. But beyond that, where does the machine learning come in? So this is where the domain of meta modeling becomes really important. And I'm just showing a framework we also built in the team at Amazon, but it's also BSD licensed, called EmuKit. That is a meta modeling framework that's designed partially with these challenges in mind. And this is the sort of tutorial webpage. But what do I mean by that? Well, first component that I've spoken about is now this sort of tube map for data, which is going to sit on top of streaming algebra. But the next thing we want to do is sort of understand how to explain what's going on. So explaining what's going on is the challenge of looking at that map and understanding why particular decisions have been made. So in the case of AutoAI, that's where we're going to go from fit models to fit systems. So meaning we're going to go from fair, interpretable, and transparent models. I prefer that to fairness, accountable, and transparent, although both accountability and interpretability are contextual, obviously, to fit systems where we're not looking at an individual model, but we're trying to explain the decision made in some composition of models. As soon as we've got that tube map, we can already start deploying sort of some classical techniques in order to prove things about our system. So classical software verification ideas, classical statistical ideas such as outlier detection. We can try and verify that a decision is not being based on any prohibited characteristic. That's actually very hard to do today in a standard software as a service because, service-oriented architecture, because in a standard service-oriented architecture, you don't know, you may be dependent on the service, but you don't know what that service ingested. So that service may have ingested a prohibited characteristic, and you may be unknowingly basing a decision you're making on a prohibited characteristic. That's the sort of thing that's quite difficult to verify. But once you've got this sort of Milan-like tube map, you would be able to verify that very quickly just by identifying where the prohibited characteristics were going into the model and then seeing where they're propagating through the model. But importantly, the sort of AutoAI agenda really comes in when we start using the type of ML techniques that people are talking about for fairness, interpretability, and transparency for the system instead of the model. So one of the things people will say is, okay, deep learning is so complex, I can't understand it. Allow me to sort of do some interpretation on what's going on this particular computer vision model. That's great and interesting, but the real problem may be whatever that model is feeding downstream. Now, once you've got something like Milan, you get in a position where, it doesn't matter whether it's a deep neural network or whatever it is, you've got some set of inputs that are affecting some decision. And you can now start to interrogate that set of inputs and that decision using the same type of techniques people are using for interpretability of deep models. So things like linearization around an operating point. This is super common in operations research, right? I've really become quite obsessed by the idea that we can't be doing anything very interesting in AI because we're not talking enough to operations researchers, because they're constantly doing these type of challenges and have mathematical techniques for doing it. So a typical thing that they have is they may have a complex model based on costs and optimizations, but they may want an explanation as to why a forecast didn't turn out to be correct in practice. And they'll do something called bridging. And that bridging is they linearize around the operating point, and then they use that linearization to build an interpretable model for what inputs affected the outcome. Makes a lot of sense, sounds extremely familiar to what people are doing with deep neural networks. Well, what we need to be able to do is deploy such bridges, as they're called, automatically. And we can't do that unless we know the software map. So you really want to be able to say, with these 6 inputs here, bridge it to this output and explain what's going on. Or you don't even need to say those 6 inputs. You just need to say, please explain why this output didn't come out as expected. And the system should automatically compile that it was dependent on these inputs, linearize around the operating point, and give you a sense of what's going on. That's the sort of question that senior managers are asking the whole time. Okay, so to me, I think that those bridging techniques and many, many others that people are doing all fit within the framework of what I would call statistical emulation. And it's a little bit sad that in machine learning, we don't pay enough attention to what people have done in these other fields. So if you look at things like linearization techniques for neural networks, then you could sort of view them as a statistical emulation of the operating point around where that input was. And you view the linear model as a valid emulator of the system in that region. Now, in general, in emulation, we tend to do more sophisticated things. So what's the idea in statistical emulation? Well, it comes up a lot when you're interested in machine learning and the physical world. So you've got some real world data, which you can measure, and the sort of thing, and that's on the right. And that might be, so like my favorite examples all come from thinking about things like Formula One. So you might be trying to design a new Formula One car, and you can see how the car performs on the track. That's your real world data. But then you also have simulators. So you have things like wind tunnels that you can simulate the car in. And you also have the ability to do computational fluid dynamics simulation. These different simulators have different qualities. And the idea in statistical emulation is that you assimilate information from these different models, different simulations and the real world, by building statistical emulators that are basically machine learning models that learn from the simulation and relate to the real world. And that gives you an ability. Why do you do this? Well, the simulations are often slow, or they require getting a car into a wind tunnel. And so if you could use the emulator to make your decisions as a proxy for the simulator, and of course, it's a very different type of emulator than a computer emulator, which is why I say statistical emulator. Then you can have a perhaps better understanding of the physics of the system. You can also build your emulator such that it's much more interpretable than the original system was. And you can do things like sensitivity analysis on it. That's all the stuff that EmuKit, that software I showed you, does for you. So in practice, this relates back to a model that's very dear to my heart because it's very common to use Gaussian process models in this domain. So for those of you who haven't seen a Gaussian process, the notion of a Gaussian process is you have some prior belief over the set of functions you're interested in. And you combine that with data that you observe in the real world and throw away all functions that don't conform to your data. Now, in the simulation case, this data is data you can actively acquire. So it's data from a simulation, or you might actually road test the car or put it in a wind tunnel. So you have an ability to control where these data points are coming in. So for example, in this case, where we have an amount of uncertainty between the two data points on the left, you might choose to take a new data point in the middle. But you would only choose to do that if it's helping you to explain the decision you're interested in at a given time. And this is the type of approach that allows you to answer questions contextually very quickly about what a large scale, in this case, it's no longer a simulation. When we go back to AutoAI, it's kind of, I mean, is it a simulation? I don't know. I'm not sure exactly what to call it. It's a large machine learning system. So we take that set of techniques and we deploy them on the machine learning system. So instead of having emulators that work on the simulation, we have emulators that interact with all these different components and make predictions about how they're performing. Like in the simplest case, what I told you was bridging earlier. A set of linear emulators would be the way that the bridging problem is being solved at the moment. But you can go towards much more complex things by using Gaussian processes. Or indeed, if you want to plug one set of emulators into another, you get what I would call deep emulation, which has the structure of a deep Gaussian process. So you can start using sort of techniques which are a bit more interpretable than perhaps your underlying forecast might be. The main point, you don't even need to know how your demand forecast was being made. It could be a neural network, it could be a Gaussian process itself, it could be a linear forecast, it could be an AR model. What you do is you just have the map of what the inputs were, what the outputs are, and then you can start to assess the quality of what's going on. So that's kind of the roadmap, that we end up using this form of emulation, but instead of being on a simulation of a system that's designed by physicists, we do it directly on the software code. And we're able to do that because we have this underlying framework, Milan, that's giving us the tube map of how the data is all interconnected together. I said I'd finish at 1:45, and I'm really keen to do that because I'm really curious about questions and comments. I'm sure we'll finish the 15 minutes afterwards. I hope it wasn't too incoherent. There's a lot there. You know, and as I said, there's just no possible way that the team I'm building in Cambridge can do on its own. I'm trying to sort of push this as an agenda that we should all be joining in on and thinking about the challenges of us. And in order to deliver on that agenda, we just have to get much closer to understanding how these machine learning models are deployed. So my argument is that AI is fundamentally just design of these machine learning systems, plugging things together. There's no magical breakthrough that means that it's going to adapt to us in ways that we haven't seen before. And we're not ready to deploy automation in uncontrolled environments because you tend to get this response from the environment where it tries to game you or surprising things happen. Until we are ready to do that, which involves totally revisiting how we're designing systems. So that's a big project in itself that I think about occasionally, but have not done any work on. Monitoring and update of that system will be key. And that's really what this AutoAI agenda is trying to do. It's trying to get it so that we can build systems that are easy to monitor. And then they're automatically monitored in practice and can be rapidly updated when something's going wrong. And with that, I'll just see if I can just quickly show you my talks page, and you'll see that at the top of that page, I've written extensive notes, which also give you some links to some of these different things. So you can see everything we've talked about on this page. So just search for Neil Lawrence talks. And you'll find all the details there and, you know, some summary of the sort of ideas about why this is a problem. And right there, I'll stop and see if there's any questions.
That's great, Neil. Thanks. That's fascinating. So I'm going to open it up to people to ask questions, and feel free to either write them in or just unmute yourself and ask a question in the traditional style.
Who's going to be first?
Well, while we're warming them up, I was wondering about how much of this, because it sounds a bit like systems engineering of complex things like, you know, aircraft and complex systems, which involve a lot of complex modeling and mathematics and inference and, you know, filtering and so on, but also have to fit into a real world scenario and involve code, and the code has to be secure and so on. So what do you think is the sort of biggest conceptual difference from that and the kind of ML embedded systems that you're talking about?
It's a great question, actually, because so one of the teams, so we did quite a lot of work on the drones, and we were, I won't go into the details of what we were doing there, but I mean, you can imagine it was within our scope of expertise. And that was so easy to do very advanced machine learning techniques within that context, because when you're doing that type of work to build an engineering system, it's self-contained. You're controlling every single part of it. And the amount of testing they were doing on their components because of the issues around, I mean, there's a lot of sort of ex-Boeing engineers there bringing in these classical engineering approaches to building a hardware product that does things in the real world. And so it was actually a lot easier to understand what was connected to what, because they don't have this same approach of construction of the software by people sort of being responsible for creation of a service where outside the bounds of this is the interface, this is your inputs, this is your outputs, they're uncontrolled in what they do. That map is constantly being monitored as part of the safe design of things, because it's clearly safety critical. The issue that we've got with these ML AI systems is they are to some extent safety critical, but we're not putting that kind of thought into the design and deployment. And if we were, we wouldn't be able to build such complex systems, because you get back to that issue of software systems that are too complex to build, like we've seen with so many failed software projects.
And I guess it'd take 20 years to build one thing.
Yeah, and you can't adapt it once it's shipped. So you know, a lot of it was sort of fascinating. You look at these systems in Amazon that have been around for 20 years, and of course, there's components that relate to what was shipped. You know, there is this evolutionary side to the system, but it's unfortunately not necessary in the robustness.
The audience are warming up, so we've got some questions. So Zohair's asked, what are the regulatory challenges associated with AutoML?
I guess, so it might mean AutoAI or AutoML there.
Yes, AutoAI, since that's what you're talking about.
Yeah, I think that it's a response to the regulatory challenges. Well, I don't even think of it as regulatory. I think putting the regulatory first is the wrong way of doing it. One of the things I'm keen to say is, look, I think it's ridiculous when people complain about the GDPR, because there's nothing in the GDPR that isn't something that you would expect a reasonable software system to do. Like, so if you look at things like the right to have your personal data deleted, companies are saying, oh, we can't do that. We don't know where we've stored their personal data. To which the follow-up is, what the hell's going on in your data systems? And which the answer is, some of the things we've talked about here, they're being built component-wise, and people aren't tracing where personal data is being stored. But fundamentally, that's bad practice. That's not bad practice just from a regulatory point of view. That's bad practice from the quality of the system that you've built, if you don't know where a customer's data is stored within your system. So if you don't view it from a regulatory perspective, you just view it from a systems quality perspective, you can just see it's crap. Same with, say, the right to explanation. If you can't explain to a customer why a particular decision was made about them, given your data, then that means you can't explain your systems. You're suffering from intellectual debt. Now, that's the sort of thing that was constantly being asked of us by vice presidents. And why has this happened? Why has that happened? So it's an indicator that your systems are broken, and they're all indicators of intellectual debt. So unfortunately, they come as this imposed regulation. Whereas I think that the first thing we should see them as is, oh, well, that's a minimum standard. So I think GDPR should stand for good data practice rules instead of general data protection regulation, because it should be like a minimum standard that your system should be capable of doing. And the fact that it's not, and Facebook are threatening to leave Europe because they can't manage to store customer data within Europe, is showing the absurdity of what's going on, even at big tech companies. So I think once you've got it in place, it helps a lot with regulation, good, efficient regulation. I'm not like massively keen on big regulation because it's pointless having regulation that you can't impose, but it helps create a dialogue between the regulator and the companies about what's actually going on in the systems and what should be going on.
So your example was protected characteristics, but if you had a system that was making inferences based on inferring protected characteristics, if it's not in your data, how would you ever protect?
Well, that's a great question, and it's still illegal. You can't indirectly use information that's associated with things like, under GDPR, things like postcode, because you can end up discriminating against a subgroup ethnically. But that's where, well, two thoughts on that. One, you kind of know some of these things are strongly correlated with protected characteristics such as postcode. But I think that's actually where you start getting really interesting input from these emulator type ideas, because the emulator itself could be monitoring that for you. So you could have the emulator hooked up to a knowledge of ethnicity, which, okay, now it's a bit difficult because you have to ask people for their ethnicity, but it can be ensuring that fair decisions are being made at the critical juncture by going in and checking over time that these decisions are fair, rather than sort of having to rely on your knowledge about each individual decision.
There's one from Hui asking, connection between AutoAI and causal inference. What's your view on the connection? Do you have to be able to do causal inference to do AutoAI, or?
It's a great question, Huey, and it relates a little bit to the next question from Ryan around ethics and explainability. So actually one of the major things that we've been looking at with these systems is, once you have a deep emulation of the type I described, you can do causal inference on that emulation instead of causal inference on the underlying software system. Now, why is that important? Well, you can do causal inference directly on the software. They would call it a simulation. So you can run your software forward and backwards on the real world data and see what this simulation would have done. Like, you can ask questions like, what would have happened if I hadn't got the pay-per-clicks in stock? And that's called a counterfactual simulation. But it's very slow to do because you're running your entire production systems to redo that. So the first thought is, well, I can use emulation in order to be able to sort of deal with that problem. And this is a sort of key aim of the AutoAI agenda, that instead of doing that directly by running the simulation, I run the emulation where I can instead. And I can do that that sort of causal question much quicker. Now that immediately starts getting you to questions about, well, what emulation is sufficient? Well, of course, it's contextual. So the right emulation, it's not going to be a one-size-fits-all emulation. You're going to have to redeploy your emulators to take into account the question you're asking, because it's contextual about which parts of that system are important to answer that question. And that's where the human comes in with their sort of understanding of what things we care about, that the system doesn't know what we care about. And this relates to explainability, because the notion of explainability without context, I mean, like, I used to constantly think about this because there's this thing called a question mark email, where you get an email from Jeff Bezos, which just copies some complaint from a customer and just puts a question mark at the top. And you have to answer, why has your systems gone wrong? Well, the answer Jeff Bezos wants is different from the answer the customer wants, is different from the answer the engineer responsible for writing that code wants, is different from the answer that all the intermediate managers between Jeff Bezos and that person wants. So explainability is contextual depending on who you are. So the notion of explainability without some kind of adaptability in terms of how to do that explanation is kind of nonsense. And that's why you can only start seeing what these questions really are if you look at these systems in the real world.
Do you think that, so if you use a Gaussian process or some regression method, then you're going to be able to emulate where you've kind of sampled the input space? Do you think some more causal mechanistic modeling would allow you to actually extrapolate a bit better to situations which you didn't train on? Or
yeah, I think the dream was, and actually Javier has got papers on this, and this is something we started talking about. I'm not on that paper, but it comes from conversations we had inside Amazon of something that I would call causal emulation. So just like you've got Bayesian optimization in standard systems for AutoML, causal emulations would give you the ability to do that type of extrapolation. So you have to say, actually, I can run the emulator here, but I'm not confident about my causal inferences in this region. So I need to rerun the simulator. I need to rerun the simulator to get more information about what would have happened if I'd run the production systems. And then I rerun that and then I answer. In that sense, you can also see that I think that might be occurring at different levels of abstraction. So you're not always going to do deep emulation. Sometimes you'll just conflate several components in a system and emulate them as one. And that to me somehow relates to, are you talking to Jeff Bezos or are you talking to the engineer that wrote the code that's gone wrong? Which level of emulation you might want.
So Ryan, if you're there, did Neil infer your question correctly, or was there anything he missed? Speak up now. Okay, so we're approaching 3 o'clock. Is there any more questions for Neil?
It's amazing. I actually managed to finish on time for once. Normally I totally overrun.
That's very interesting. I still haven't worked out what to do in these seminars to thank people. I could do really
if you can use
everyone.
PayPal to send them money, or Amazon gift tokens, you know, things like that. They're great.
Yeah, that happens if you give talks in America. So give some talks.
Right?
I'm going to recommend you give talks in America and you'll get paid for it. That's my way of paying you with advice. I'm going to give you a clap anyway.
Thanks very much. It was great. Really sad I can't be there, but you know, I have such affection for Manchester and Magnus and the Data Science Institute. It's really nice to have been there virtually, even if I do not now get to have a 3-hour train journey back through the Peak District and via Sheffield.
It's really interesting. Thank you very much. And Neil's shared details about his website, lots of interesting notes about this stuff. Looks really fascinating. So go and drill down into it. And I'm sure Neil will be happy to answer questions after. If you can let me have them and I'll pass them along to him, or you can try and email them directly. I don't know if he does email, but I don't.
What's that?
Okay.